In the last class, we did de Broglie wavelength and Heisenberg's uncertainty principle, and both were part of quantum mechanics. So what we are going to today is we are going to do quantum mechanics in a formal way. So today we are going to do quantum mechanics in a formal way. So last class we did de Broglie wavelength and Heisenberg's uncertainty principle, which are part of quantum mechanics. So today we are going to do quantum mechanics in a formal way. Formal way means in a methodical way. So why quantum mechanics? So that is the question you may ask first, that we have already addressed to some extent. So why quantum mechanics? What is the need for quantum mechanics? And we saw that one of the examples, like for the need of quantum mechanics, was that the hydrogen spectrum physicists were unable to explain the hydrogen spectrum using classical physics or Newtonian physics and electrodynamics. Why quantum mechanics? Because we know that hydrogen spectrum that we have already done. So we are going to stick to this example. So hydrogen spectrum cannot be explained using classical physics. By classical physics we mean Newtonian physics, Newton's laws. So classical physics means Newton's laws and electrodynamics. Or more basically we can say that at the microscopic level, microscopic level means when we are dealing with electrons and atoms. Quantum mechanics is the theory. Quantum mechanics or quantum physics is the theory, to work with. Okay. So at this microscopic level, what happens is that Newton's laws and electrodynamics does not work. So what we need is a new physics, and that is quantum physics. And the new physics and the concept of new physics was first given by Bohr through was given by Bohr through his model of hydrogen atom, which is not a complete model because it had its drawbacks. It could only explain partially the hydrogen spectrum of hydrogen X spectrum, but nevertheless it was a start. So in quantum mechanics, what is important? So we are going to lay down the postulates of quantum mechanics. So in quantum mechanics, the state of a quantum mechanical system, say a particle or electron, is completely defined by its wave function. Okay, it's completely defined by its wave function. This wave function is generally defined by psi, which is a function of position vector and time, right? And we just go through it. So it's a function of position coordinate r and time. So this is important. So when we say a quantum state, before we have used that the particle is in quantum state. So when we say quantum state, that means when we say quantum state, okay, so when we say quantum state, we mean a wave function. So we can so any particle is in a definite quantum state, means it has a definite wave function psi, which is a function of r and t. That's what it means. Like in classical physics, like in Newton's laws, what was there? In Newton's laws, if you're using Newton's laws or Newtonian physics, then how do we define a particle? A particle is defined by its position r and momentum. That will completely define the particle in Newton's laws. If you know the position of the particle and its momentum, the particle, everything is known about the particle. In quantum mechanics, the wave function carries all the information. So this is important. This is the wave function that carries all the information about the particle. Okay, it carries information. So it's a wave function. So we saw that in Newtonian physics, r and p can be found out exactly. That is, there is no uncertainty in the position and there is no uncertainty in momentum in Newtonian physics, because there is no so del x is 0 and del p is 0 in Newtonian physics. But we saw that in Heisenberg's uncertainty principle, del x and del p cannot be simultaneously 0. So we need a new way of defining the state of a system in quantum mechanics, and that is the wave function psi. And what is the importance of this wave function? So what is the physical importance of this wave function? The physical importance is that the psi star dv is the probability that the particle is found in a small volume dv. Since the particle has to be somewhere in the space, psi star dv is equal to 1. So what do we mean by this? So if we have a particle, so we have a psi, and psi can be a complex number. So this is important. So this is a theoretical construct. Psi is a complex number, can be. Maybe it's a complex number. If it's a complex number, it can have its complex conjugate psi star. What is psi star? Psi star is the complex conjugate. Complex conjugate. So what is the interpretation? So the question is, what is the physical meaning of? So what is the significance of psi? Significance, what is the significance of psi? Isn't it? So I am telling you that the quantum state is given by psi. So what is the physical significance of psi? So it means that, so if we consider one dimension, then your psi star dx. So we are considering one dimension, we are not considering say 3 dimension, just for the sake of simplicity. Then this is the, so now comes the question of probability. So this is the interpretation. So this is the probability of finding the particle between x and x plus dx. Remember, so that means now the particle can be, in general, can be anywhere. So this is, so let's draw it. So this is, my psi. This is, so psi star is known as the, and this is my x. So this is psi star and this is x. So it means, so it could be like this, it could be like this. So psi star is the probability density, is called the probability density. Okay, is called the probability density. So if this is x, okay, this is slightly exaggerated, this is x, okay, and this is x plus dx. Then the probability of finding the particle between x and x plus dx is this shaded area. Okay, and this is, value of this is psi star x. That's what it's telling. So what it's telling is that the particle, we cannot say with certainty where the particle is. It can, so it can be like that. So the particle can be anywhere between, so this is minus infinity and this is plus infinity. So the particle can be anywhere between this, okay, anywhere. But we can say the probability of finding the particle between x and x plus dx is psi star dx. So psi star is called the probability density. So this is the probabilistic interpretation of the wave function. So this is very different from what we have learned in Newton's laws. Newton's law, there is no probabilistic. There is no question of probability. But in quantum mechanics, where the particle will be, we may not be able to tell certainly, but we can give the probability of finding the particle in a certain region. So this is the probabilistic definition. This is the probabilistic definition of psi, or interpretation of psi. We should not say definition, we will say interpretation. Interpretation. Okay. This is the probabilistic interpretation of psi. So this is what we have written here. So here I have written in 3 dimensions. So psi star dv. dv is when I say in 3 dimension, then we say dv. Otherwise, since I was doing in 1 dimension, I wrote dx there. So this is the probability that the particle is found in a small volume dv. Okay, and since the particle has to be somewhere in the space, then this integral over the whole space should be 1. So what do I mean by this? So since the particle has to be somewhere between minus infinity and plus infinity, then this psi star, this is the probability of finding the particle between x and x plus dx, but the particle has to be somewhere in minus infinity to plus infinity. So this is equal to 1. So that's why this is called. So the total probability has to be 1. So this is 1. So what we say, so what is the meaning here is, if the wave function is psi, and if I try to measure the position of the particle, then as I have seen, as shown in the picture, the particle can be anywhere between minus infinity and plus infinity. Okay, so suppose this is x. Okay, this is x. Okay, this is x. Suppose when I measure the position of the particle having the wave function psi, I can find it here. Okay, so again I create the particle in this state psi and I measure its position. So this time I may find it here. So I keep doing like this. So next time it may be here, and again somewhere again it may be here, it may be here. Okay, so every time I create this wave function psi and measure the position of the particle, I will see that the particle may be occupying different positions. But you can see here the probability of finding the particle is maximum in this region. So if we keep doing the experiment, we will see that, say, around this region, there will be, most of the time you will be finding the particle around this region. And sometimes you may be finding the particle to the right of this region, okay, and sometimes you may be finding the particle to the left of this region, but most of the time you will be finding the particle around this region. So that is what this wave function gives. So once we know the wave function psi, we can find the probability density, and from probability density we can find out what is the probability of finding the particle between x and x plus dx. Okay, and that is given by psi star dx. And since the particle has to be there somewhere between minus infinity and plus infinity, what we have is this expression. Psi star dx is equal to 1. So this is important. So this is called normalization. So this is what we are doing. We are laying the groundwork of quantum mechanics. This is the postulates of quantum mechanics. That what is the interpretation of? So there has to be a psi, and psi star gives the probability density. What else is there? And so we have done this part. Now comes this part. In quantum mechanics, the observables in quantum mechanics are operators like x for position x, px for momentum along x, energy E for energy E. Okay, so what it's telling is very different from what we have done in Newton's physics. In Newton's physics, what we have done is we have done R and P. This gives the state of the particle. Okay, state of the particle. So if we do a measurement, we will find out R, and we can also find out P at the same time without affecting the other. So R can be exactly found out and P can be exactly found out in Newton's physics. But in quantum mechanics it's different. So here, so instead of R we can write X and P. So in quantum mechanics, keep it in one dimension. So in quantum mechanics, what it's telling that these are observables like x, px, energy. So these have to be represented by something called operators. This is important. So this is operator. So this concept of operator comes. So if you want to measure, so theoretically, if you want to find out the position, you have to use the operator x. And if you want to find out the momentum, we have to use the operator px. Okay, so this operator is used to extract information. So this operator is used to extract information from the wave function. Okay, so this operator is used to extract information from the wave. So wave function is given. So from wave function we have to get some information. So this is what we use. These are operators. So what is an operator? Like example of operator is operators are not numbers. So example of operator is like ddx. Okay, So ddx is an operator. So ddx acts on something and changes it. Right, so this is an example of an operator. Or d2x dx square. These are examples of operators. There can be other types of operators. So these are examples that you have already done. You have done, you know how to differentiate once, you know how to differentiate twice. So these are all operators. Okay. So it acts on something and changes it. So here also what it's telling is, here we will take x as an operator. Okay. Px is an operator. So in certain x operator can be written as just x, while px operator it is written as minus h bar ddx. This we don't have to worry. So this is how it is. So x operator is x and the px operator is minus ih cross ddx. So the measurement of any observable in the state psi can give only certain values, which are called eigenvalues of the operator corresponding to the observable. Okay, so what we said is the measurement of any observable in the state psi can only give certain, it can give only certain values, which are called the eigenvalues of the operator and corresponding to the observable. So we have already done this before. So suppose as a just like x, if you measure the position x, if you measure the position x, so now we are now talking a quantum mechanical particle and position x for wave function psi. So it's in some kind of wave function, and if you measure this some state, so position for x, so we refer it to this state as psi. Okay. So this is how we write it. It's position. So this is a quantum mechanical state. So if we measure the position in this quantum mechanical state, okay, and if you measure the position in this quantum mechanical state and you will get values. So position x for psi, then you may get various values x1, x2, x3. So you will keep getting various values. Okay. So these are called. So these are the different values you are going to get. X1, x2, x3, x4, x5. So when you measure the position if the particle is having a wave function psi, then you may get different values x1, x2, x3, x4, x5, etc. You can keep getting this. But if you keep getting only one value, like if only one value occurs, say x1, okay, if only one value, say x1, then we will say x1 is the eigen value for the wave function psi. Okay, if you keep getting different values, then obviously we cannot say that x1 is the eigenvalue of psi, or x2 is the eigenvalue of psi, or x3 is the eigenvalue of psi. But if we keep getting only one particular value, say x1, whenever we do the measurement for the particle in the wave function having the wave function psi, then we will say that x1 is the eigenvalue for the wave function psi. So same with momentum also. Same with momentum. Here I gave the example of position. Same with momentum. Same concept with momentum. So if you are measuring the momentum and you keep getting only one particular value of the momentum in that particular quantum state, then we will say that that value of the momentum is the eigenvalue for that quantum state. Same with momentum and same with energy. Okay, same with momentum and same with energy. Okay, that means so if we keep getting the same value of if we keep getting the same value of momentum, if we keep getting the same value of momentum, say P1, when the particle is in a particular quantum state, particle is in a particular quantum state, when the particle is in a particular quantum state, if we keep getting the same value of momentum, say P1, when the particle is in a particular quantum state, then P1 is the eigenvalue. P1 is the eigenvalue for the operator Px corresponding to the quantum state. So this is the eigenvalue of the operator corresponding to the same quantum state. Here also I should have written then only one values, then x1 is the eigenvalue for the wave function psi. Here I should have written eigenvalue So here I should have written eigenvalue for the operator x corresponding to psi. This is the eigenvalue for the operator corresponding to psi is called the eigenfunction. Okay, corresponding to psi is called the eigenfunction. Is called the eigenfunction. Okay, this is called the eigenfunction. Here also, here it will be psi will be the eigenfunction for the momentum. Here psi will be this quantum state will be the eigenfunction for the momentum, having the value p1. So this is what is meant here. If if every measurement of the observable gives the same value, then psi is the eigenstate of the operator or the observable. That is the important thing. So in that case, there is no uncertainty in the observable. So because every time we measure the observable, we get the same value. That means there is no uncertainty in the observable. Uncertainty is 0. And obviously there is a concept of average. So here x is some observable. So observable means it can be represented by an operator. So this is an operator. This is an operator. So the average value of x. So if we consider a wave function psi, and if we measure the observable x, we will get different values. We may get x1, we may get x2, we may get x3, so on and so forth. So from here, experimentally we can find out something called mean. Okay, isn't it? What is mean? Mean is whatever we mean is x1 plus x2 plus x3. So we continue like this, divided by n. N is the number of observations, and that will give us the mean. So this is experimentally. So this is experimentally. This is experimentally. Theoretically, there is a method. This is using the operator. So you sandwich this operator between psi star and psi and integrate over the entire volume, and what you get is this. So this and this should be the same. So the average of the operator is given by minus infinity to plus infinity. You sandwich this operator between psi star and psi, and what you get is the average. So these are the postulates of quantum mechanics. And the most important part is that the quantum mechanics, like in Schrodinger's, we have the Schrodinger's equation. The Schrodinger's equation, so Newton's law. So Newton's equation we know, Newton's equation becomes, in Newtonian physics we use Newton's equation of motion. Newton's equation of motion, obviously it is not valid in quantum mechanics. It becomes something very different. what we have in quantum mechanics is Schrodinger equation. Schrodinger equation. Okay, and this tells us how. So this is my Schrodinger equation. H bar, I is complex number, I we know is equal to root of -1. Del psi del t is equal to H psi. So this is a differential equation. We don't have to worry about this. So from here we can find out psi. For the theoretical physicist, you can find out psi. So from this, find out psi. This is a differential equation. This is called the Schrodinger's equation. H bar we know, del psi del t. So where psi is a function of x and t is equal to H is an operator. What operator? Is the total energy operator. We don't have to worry about how it looks like. So this is a total energy operator, and what we get here is the famous Schrodinger's equation. So this is the central equation of quantum mechanics, Schrodinger equation. Just like in Newton's laws of motion, we have Newton's equation of motion. In quantum mechanics, we have Schrodinger's equation. So in order to find out the wave function for a certain particle, what we have to find out is we have to solve this Schrodinger's equation. So I'm going to end now, and we will continue in the next class. Thank you.